Hello everyone, welcome to this lecture on droplet vaporization and combustion. This lecture was not there last year. This has been added based on some requests from the discussion. The students who had given some requests on the discussion forum that some introduction to droplet vaporization and combustion would help them understand combustion processes in liquid propellant rockets and other liquid fuel combustion systems in a better way, and that is the purpose of this lecture. We will take a brief look at the process of droplet vaporization and combustion. The best way to understand and appreciate droplet combustion is to see videos of droplets burning before we get into the equations. So let us start with that. The video that I am going to play will show a series of snapshots of droplets of various fuels burning in air. Let us get started. So, droplet combustion is an important process that occurs in all combustion systems with liquid fuels like burners, reciprocating engines and gas turbines. Here it is captured by burning droplets on a quartz fiber at normal gravity conditions. You will see burning of 4 fuel droplets, first starting with ethanol. Now you will be able to see it better. Next is gasoline. Next comes kerosene. Finally, diesel. Now you will see all 4 in a single frame, and notice the transparency of the ethanol flame, and that is played at a slower speed. Good. So I will just go back to one particular frame where I want you to notice something. Okay. Notice the following. See, you have an ethanol droplet and you see an inset graph. The graph on the, do not worry about not being able to see the numbers, that is irrelevant. What I would like you to notice is that the whatever is plotted is close to a straight line. In all the 4 graphs, whatever is plotted is a straight line, and now I will tell you what exactly is plotted. On the x axis is the time, and y axis is the square of the instantaneous droplet diameter. Let me repeat that. The x axis is the time and the y axis is the square of the droplet diameter. And what do we notice in all the 4 cases? It is that the diameter squared as a function of time is a straight line. Okay, and this is the most important input that one needs in designing liquid fuel combustion systems. We will see how. Okay. And before we move on to that point, I would like you to remember this frame also, where for all the 4 cases the droplet diameters and the corresponding total burn time is also compiled. For ethanol, well, let me not go one at a time. All I want you to notice is The droplets are all approximately about 2.5 millimeters in diameter, which is what is used in this experiment. The burn time varies from something like 2.6 seconds to about 3.6 seconds. Please keep these numbers in mind, we will use it again. Okay. Let me now go on to a discussion of why the d square versus time being linear is crucial input for design of liquid fuel combustion systems. Okay. The reason is very simple. The typical residence time that is available for the fuel to burn in a liquid fuel combustion system is a few milliseconds usually. So, typical residence time is 3 to 5 milliseconds. Okay. And what did we see now? We saw that the diameter squared as a function of time, okay, is equal to some constant multiplied by time. Remember that what we saw in the video is the diameter as a function of time squared plotted as a function of time looked like this, right, it is a straight line. So, this equation is nothing but d square is the initial diameter squared minus some constant multiplied by t. This is called the famous d squared law of droplet vaporization and combustion. Okay. Therefore, the diameter is proportional to time. I should be a little careful. It is proportional. There is proportional to kT, and you start with an initial diameter of d0. So, it will at t equal to 0, the diameter will be d0 squared, and it will slowly burn, and the diameter squared will vary linearly with time, and at some point the droplet will be burnt out. When the droplet is burnt out, its instantaneous diameter is 0. Therefore, starting from this equation, d square at time t is the initial diameter squared minus kT. Now, the diameter at burnout is 0, all the droplet is burnt out is 0, and the corresponding time is the vaporization time, which we will call T subscript V, and therefore, the time for vaporization, you plug this into this equation, put d equal to 0, time for vaporization becomes initial diameter squared divided by k, some constant called the vaporization constant. This d square law is an experimental fact. The next, now one might wonder, it is not just droplet vaporization that is happening inside a combustion chamber. There are several other processes that happen, as you would have learnt in this course from the earlier lectures. The fuel and the oxidizer have to mix, and then that has a certain time scale, and then it has to undergo chemical reactions, and that has a certain time scale. But why are we so focused on this particular process and not on mixing and chemical reaction? The reason is very simple. We have three time scales: the time for vaporization, the time for mixing, and the time for chemical reaction. Okay. Without going into too much details, I just want to tell you that amongst these three processes, the time for vaporization is the largest. It is the slowest process, and therefore it takes the longest time, and therefore is rate limiting. So, it is the vaporization time is rate limiting. It is the slowest process, and therefore when you design the combustion chamber, you need to make sure that enough time is provided for the droplets to completely vaporize. Otherwise, you will have fuel droplets entering the combustion chamber and leaving without completely burning, which is something that we do not want. And if you ensure that there is enough time for the droplets to vaporize, you have automatically ensured that there is enough time for mixing and reaction, because both mixing and reaction are much faster than vaporization. Okay. So this is the reason why the recognition of the simple experimental fact, that is the d square law, is crucial for the design of liquid fuel combustion systems. Okay. Moving on. Now what I am going to do in this slide is, you recall, maybe I will show it one more time, this slide where what we have compiled is the droplet diameter and the burn time, and what do we know? Burn time goes as d0 squared divided by k. I am going to compile all these numbers in the form of a table. Okay. Let me remind you that, remember this formula which I am marking with a star, time for vaporization is equal to d0 squared by k. Okay. Maybe I will write this again, Tv is d0 squared by k. Remember this. Now I am going to compile all the information. Fuel d0 in millimeters, time for vaporization in seconds, and using this information I am going to calculate k, which is d0 squared by Tv. It will have units of millimeter square per second. Well, in some places you will find that the definition is the way k is defined is the reciprocal of how I have defined, but as long as you maintain consistent units you should not have any problems. In some places you will see that k is defined as Tv divided by d0 squared. So anyway, that is just a convention, let us not worry about it here. Fuel d0 Tv. Let us take ethanol. This is the first video that you saw. The diameter is 2.45 millimeters. The time from the experiment is 3.6 seconds, and therefore you can calculate this 1.66 millimeter square per second. Diesel, the diameter was 2.63 mm, burn time was 3.44 seconds. So the vaporization constant is 2. Gasoline, okay, the diameter was 2.65, burn time was 2.6 seconds. So this would be 2.5 millimeter square per second. Finally we saw kerosene, again 2.43 mm, time it took was 2.88 seconds. You can calculate, you will get something like 3.3. Okay. You can cross check these numbers by plugging in the details from the videos. The first thing I would like you to notice is that the variation in this is not very large. It goes from something like 1.6 to 3.3, just a range of over a factor of 2. Okay, so this number does not change a whole lot, it is roughly the same for all the fuels. Okay. Keep this in mind. Now we will use this information and maybe erase. Okay. Now let us go back to what kind of residence times are available, and from the evaporation constant we can calculate what size of droplet sizes are allowed. Okay. We saw earlier that the range of residence time is between 3 and 5 milliseconds. Okay. So let us take 3 different cases. Let me take 1 just as a lower limit, and then 1 millisecond, 3 millisecond and 5 millisecond. Okay. Now you can calculate what is the maximum allowable diameter from this information, which is the time it takes for, see, the time it should take for the droplet to vaporize should not exceed 1 millisecond in the case of this, 3 milliseconds in this case, and 5 milliseconds in this case. So from this formula you can calculate what is the diameter allowed. From here you can calculate d0 is equal to square root k TV. For TV equals to 1 millisecond, 3 millisecond and 5 millisecond, calculate D0, and for the purpose of this calculation we will assume that the fuel of interest is kerosene, which has an evaporation constant of 3.3 millimeter square per second. Plug in the numbers and calculate D0. So, the maximum allowable diameter for the 1 millisecond case is 60 micron, for the 3 millisecond case is 100 micron, and for the 5 millisecond case is 130 micron. What are these numbers? These are the maximum allowable droplet size. Anything larger than this will go out of the combustion chamber without completely burning, and we do not want that. Okay. So, two numbers I would like you to remember, which will come in handy when you are doing back of the envelope calculations. One, evaporation constant in units of millimeter square per second is a number that is roughly between 1.5 and 4. Okay, that is a good number to remember, and when you use, and the residence time that is available in a liquid fuel system is usually a few milliseconds. Combine these two information, you will know that the maximum allowable droplet size should be roughly about 100 microns. It cannot exceed 100 microns. These two numbers, the third one you can calculate from the first two. The two numbers are useful to remember. And how did we get these numbers? By simply extracting this information from a set of simple experiments that were done with droplets. Moving on. So, liquid fuel combustion systems. We will take the 3 millisecond as a reference number to work with, and for 3 millisecond the maximum allowable diameter is 100 micron. Okay. So, taking the residence time TR as 3 milliseconds, D0 max is 100 micron. And this is the reason why you have sprays and why you need spraying or atomization, and why you need injectors that can convert liquid fuel or jets or sheets of liquid fuels into small droplets. If you do not do that, you will have chunks of liquid fuel with sizes much greater than 100 micron. There isn't enough time for those droplets to burn inside a combustion chamber. That is the reason why you need fine sprays. Okay. So, that is why you need an injector to atomize the fuel. Atomization is a process of breaking down a liquid jet or a liquid sheet into finer droplets. Fuel into a fine spray. Okay. Now, it would be great if we could build an injector that will give us a uniform size of, let us say, 90 microns or 50 microns, but that is not how the process of atomization works. There is a certain randomness associated with the process of atomization, and therefore what you actually get is are droplets over a range of sizes, and the droplet size is usually distributed in a log normal fashion. So, if you plot the cumulative distribution function and take this, let us say, is the 100% limit, what do we want? We do not want any droplets to be larger than 100 micron. So, we want a distribution that goes something like this. It should hit the 100% before reaching 100 microns. Okay. So, this is a preferred distribution. Okay. For this example that I have assumed, where the residence time available is 3 milliseconds and the fuel that is being used is kerosene. You can try 5 milliseconds with ethanol, 1 millisecond with gasoline and so on and so forth, but the procedure remains the same. So the summary is vaporization time is proportional to the initial diameter squared, crucial. Residence time available is less than 5 milliseconds, okay, which implies D0 max is typically about 100 micrometer, okay, and the average size, this is maximum, recall that 100 micron is the maximum size, but there is a distribution of droplet sizes because of the randomness associated with the process of atomization. Average sizes will be of the order of 40 micron. Okay, so this is the summary. Okay, so 40 micron will fall somewhere here, or what is called the Sauter mean diameter, 30 to 40 micron. Okay, you can take, for example, a diesel engine. The injector, the diesel injection orifice dia itself is about 300 micron. Very high pressure sprays, thousands of bars. Common rail diesel injection systems work at 1000, 2000 bars. Okay, at such high speeds, when fine jets are injected, they just disintegrate into droplets of very fine size, and that is crucial because unless droplets are broken down, I am sorry, the liquid jet is broken down into fine droplets, combustion will not be complete, leading to unacceptably high levels of emissions, particularly soot, the black smoke that you see usually from city buses. The reason for that is poor combustion. So the average diameter should be, in this case, is 20 to 30 micrometer. Take a gas turbine engine. Orifice dia is larger, is 700 to 1000 micron, but you would still end up with a D0 bar or an SMD of 30 micron. The way it is such fine droplets are achieved in gas turbine engines is the liquid jet is converted into a thin sheet of liquid by swirling it, and then this thin sheet is broken by impinging high speed air jets on it. In that process, the sheet breaks down into droplets of very fine sizes, and this is also crucial to ensure complete combustion and minimum emissions. Liquid propellant rockets, not as stringent as diesel engines and GT engines. Injector diameters can be large, a few tens of mm. Okay. Either impinging injectors are used, jets of, see here usually the oxidizer is in liquid form, the fuel sometimes is in liquid form. In cryogenic rockets, hydrogen is in gaseous form after regenerative cooling. So some combination of the injectors used are not of the same kind as what is used in diesel engines and GT engines. It's slightly different. It's either impinging jets. If you have both oxidizer and fuels in liquid form, you create jets and make them impinge, and the process of impingement breaks the jets into finer droplets. That's called impinging injectors. The other type of injector is called a coaxial injector, where you have coaxially flowing, one component is gaseous, usually the fuel is gaseous, the oxidizer is liquid. In the cryogenic system, for example, the semi-cryogenic system, the fuel is liquid, the oxidizer is gas, and therefore the shear between the coaxially flowing jets breaks the fuel or the oxidizer, depending on which system you are looking at, into finer droplets. Perhaps droplet sizes need not be very small, even 100 microns, 200 microns are acceptable because there is time available for the combustion. So D0 can be of the order of 100 to 200 micron. D0 bar. Okay. So that sort of completes the discussion if we accept the fact that we believe the experimental observation that d0 squared varies linearly with time. But we would like to go one step further and ask, well, I see that in experiments it is clearly d0 squared varies linearly with time, but I wonder why. What processes control droplet vaporization, and why should it be such that d0 square varies linearly with time? And that is an important question, and there is a very simple way to answer. Why d0 square is proportional to t? It is an important question, and the answer is very simple, as we will see. Imagine a droplet, for instance of 100 micron ethanol droplet flowing into a combustion chamber. What happens to it? Let us say this is our ethanol droplet. It is flowing into it is inside a combustion chamber, and therefore it is surrounded by hot gases at a very high temperature, let us say at combustion temperatures Tf. Okay. Let us say the droplet diameter is d0. The droplet is injected, let us say at 30 degrees Celsius or 25 degrees Celsius. It enters the combustion chamber. The droplet temperature rises to the boiling temperature, and once boiling temperature is raised, it starts vaporizing. Even before that it will start vaporizing, but at the surface the equilibrium temperature is maintained. But for simplicity I will assume that the droplet is at boiling temperature. This is not without loss of any generality. You can assume that it is at a temperature lower than the boiling temperature, and a slightly more elaborate analysis is needed, but the answers do not change a whole lot. The principles and the general features remain the same. So you have a droplet of ethanol at boiling temperature inside a combustion chamber surrounded by hot gases. What happens? The hot gases transfer heat to the droplet. And how is this heat made use of? The heat vaporizes the droplet. So the rate of vaporization of the droplet, okay, which I will call m dot double dash f. M dot refers to the rate of vaporization, the double dash refers to the rate of vaporization per unit surface area of the droplet. It is the flux, it is the vaporization flux of the fuel multiplied by the latent heat of vaporization is equal to the heat that it receives from the surrounding. It is as simple as that. And predominant mechanism of heat transfer in combustion chambers is convection. It is a little bit of radiation, but it is not important in this case. Okay. And the convective heat transfer operates between the flame temperature and the boiling temperature. I am simply using the Newton's law of, it is called the Newton's law of cooling, but here I am applying it to heating process. So it is the Newton's law of heating. This simple equation, what does it say? The droplet is vaporizing at a certain rate, and what is the rate at which it is vaporizing? That rate is dependent on two things. One, how much latent heat is required to vaporize a kilogram of the droplet, and how much heat is being transferred from the hot gases to the droplet. That is it. Okay. And now what is H? H is the convective heat transfer coefficient, and how can we get H? Usually use Nusselt number correlations to get H, right. So Nusselt number is H d by lambda, which is the thermal conductivity, is Nusselt number, but the Nusselt number here is slightly different from the Nusselt number you would have studied in normal heat transfer. In normal heat transfer, for example, flow over a flat plate, which you would have studied in your UG, you have a plate at let us say Tp and air flowing past it at some T infinite. Let us say the plate is hotter than the air, heat is transferred from the plate to the cold air through convection, and then you say H d by lambda is Nusselt number, which is some function of Reynolds number and Prandtl number. This is what we do in normal heat transfer, but here it is slightly different. Why? It is not just heat transfer from hot gases to the surface of the droplet. The droplet is actually vaporizing, so it is giving off vapors from the surface. vapors of fuel are coming off from the surface. It is as if through the flat plate you are injecting some flow into the boundary layer, and this affects the temperature profile close to the plate, and therefore it affects the Nusselt number, and therefore the Nusselt number in this case is written slightly differently, which is as a product of two terms, which is the Nusselt number in the absence of evaporation multiplied by the Nusselt number change because of the presence of vaporization, okay. And therefore H is Nu0 Nu by Nu0 times lambda by T. This Nu0 is again a function of Reynolds number and Prandtl number. What is Nu by Nu0? We know that it should depend on the rate of vaporization, and we will see what it means, okay, a little later. Let us continue with the derivation on this side. Now I am going to substitute this into our original equation for vaporization rate, which is m dot double dash F multiplied by the latent heat of vaporization is equal to H, which now becomes Nu0 by Nu by Nu0 lambda by D multiplied by Tf minus T boiling point. Okay. Now we can rearrange this. From here you will simply see that m dot double dash F is equal to, I am going to multiply and divide by Cp for reasons that will become clear. So lambda by Cp, I am dividing by Cp here, I will bring in Cp somewhere else, 1 by D, okay, Nu0 multiplied by Nu by Nu0, okay. The Cp that I divided, I am multiplying here, Cp Tf minus T boiling point divided by the latent heat of vaporization, which came from the left hand side, okay. This quantity is called the transfer number. Denoted as B, okay, and without proving, I want you to accept this fact that the effect of vaporization on the Nusselt number is a function of B, and that function under some simple circumstances is logarithm 1 plus B by B. Do not worry about the details, just remember this as a fact. If you go back and check any standard textbook on combustion, you will find out why this is so, okay. And now we can substitute all of this into this, and finally you get m dot double dash F is equal to lambda by Cp 1 by D Nu0 logarithm 1 plus B. The B that was already there got cancelled with the logarithm 1 plus B by B, and this is the expression for the rate of vaporization. Oh, but hold on, you said you are going to prove why D0 square goes linearly with time. You have not gotten there yet. You have just shown that the rate of vaporization per unit surface area goes as 1 by D. How can we use this to show that D0 square goes linearly with time? And that is what we will do next. It's very simple. Remember this, m dot double dash F is lambda by Cp Nu0 by D logarithm 1 plus B. This is the rate of vaporization per unit surface area, okay. Now how do we calculate, how do we prove that D0 square goes as time? Very simple. You have a droplet which is vaporizing, giving off vapors. We know at what rate it is giving off vapors, which is m dot double dash F. So because it is vaporizing, its mass will decrease with time, and at what rate? Exactly the vaporization rate multiplied by the surface area, 4 pi r squared, okay. I think it will be easier to work with diameter, so I will not use r square, I will use just pi d squared. We already know the formula for m dot double dash F, and mass we know is density multiplied by volume. So, density is constant rho L and volume is d by dt of volume of a sphere is pi by 6 d cube. Do not confuse the d for the derivative with the d for the diameter. I could have used a different formula, but different notation, but I did not. Is minus m dot double dash f pi d squared. Continue the derivation. You have pi by 6 d by dt of d cube is 3d squared d. I think I am creating confusion by using d. Let me use uppercase d. d d by dt is equal to negative m dot double dash f pi d squared. Some terms will cancel, the pi cancels out, the 3 cancels with 6 giving a 2, 1 d will cancel out. So, we are left with d d dt is negative m dot double dash f, which I will substitute from here, is negative lambda by Cp nu 0 by d. I have to use capital D because we are now using d for diameter, logarithm 1 plus b. What are all the terms that come from the right hand side? You have a 2 and nothing else. We have 2 divided by rho L is what is coming from the left hand side, and on the right hand side we had 1 d, right. I think I have the mistake I made is the derivative of d cube with respect to time is 3d squared, not 3d. So, the d square would have cancelled out, we will be left only with 1 by d. Okay. So, that d will not be there, and now the d square law is staring right at our face. Take this d to the left hand side, you have d dt is minus lambda by Cp nu 0 logarithm 1 plus b 2 divided by rho L. D dt is d by dt of d square by 2 is minus lambda by Cp nu 0 logarithm 1 plus b 2 by rho L. Notice that everything on the right hand side is a constant. Therefore, we can integrate this equation. So, d square by 2 will be that constant which is sitting on the right hand side, which is negative k multiplied by t. There you go, d square law. Okay. And now you can identify what k is and what the vaporization time is. Vaporization time is d 0 squared by 4 lambda, actually it will be 8 lambda because there is another additional 2 sitting there, 8 lambda by rho L Cp nu 0 logarithm 1 plus b. This is our d square law, which we have gotten from very simple arguments. It looks like I may be wrong, you please recheck the algebra, this is still going to be only 4. Okay. That is it, that completes our discussion of d square law. I will just give you one simple example of combustion of ethanol in air. K from experiment, how much was the K from experiment? Let me go back and check. The K from experiment for ethanol was 1.66 millimeter square per second. Okay. Now, we have a formula for the evaporation constant from our simple analysis. Let us plug in the numbers for ethanol in burning in air and see if we get the right answer. What is the value of K from our simple analysis? It is rho L Cp divided by 4 lambda nu 0 logarithm 1 plus b. Okay, I am sorry, this is not k, this is k inverse. Okay, and remember that b is Cp Tf minus T boiling point divided by the latent heat of vaporization. Values for ethanol density is 790 kilograms per meter cube. Thermal conductivity of the gases surrounding this is approximately 0.08 watts per meter Kelvin. Specific heat value is 1184 joules per kg Kelvin. Latent heat of vaporization for ethanol is 846 kilojoules per kilogram. The boiling point of ethanol is 78.4 degrees Celsius, assuming a flame temperature of 2000 degrees Celsius. Now we can calculate K. The transfer number will turn out to be around 2.4. The Nusselt number is 2 plus 0.5, a correlation which is very commonly used. Grashof number, Prandtl number, power 1 by 4. I am using Grashof number because this is ethanol burning in air under free convective conditions. This will give you an Nu 0 of 5.5. Plug in all the numbers, you will get K ethanol air to be around 2 or something like 2.2 or something. Just calculate and check for yourselves. How much did we get from experiment? 1.7. How much did we get from a very crude, very simple analysis? 2.2. This is excellently accurate approximation. Okay. I hope through this lecture you would get a good appreciation for the process of droplet vaporization in a combustion chamber, and I also hope you will go back and check combustion text to understand why Nu by Nu 0 is logarithm 1 plus b by b. The key words that you should use for the search is the phenomena of blocking effect. This Nu by Nu 0 is called blocking effect. Okay, go back and check. If you have questions, let us know through the discussion forum. I can give you a little bit more information about the blocking effect. Okay, that's about all I have. Hope you will enjoy the rest of the course. Hopefully we will meet soon in a live session. Thank you very much.